So my population is composed next year of individuals that arrived and individuals that were there and didn't go anywhere. This is the proportion 1 minus m. So if next year I have 200 individuals, 50 of them came from someplace else and 150 didn't, then m is 50 over 200, or 1/4, and 1 minus m would be 0.75, or 3/4. Okay? Individuals that arrived, individuals that didn't move at all. All right, so now let's just do a little bit of math associated with that. Okay? All right. Okay. Actually, let's leave that there just until I get started. Okay? All right, now, the frequency on the island, because that's what I'm interested in right now, next year. Normally I do a subscript 1. Today would be subscript 0. Tomorrow, next year, would be subscript 1. But I can't do that because I've subscripted it as an I, so I'm going to use a prime to indicate next year. So the population next year, its allele frequency, specifically the big A allele frequency, is going to be equal to the proportion of individuals that didn't move, they're still there, multiplied times their allele frequency, plus the proportion of individuals that did move times their allele frequency. Right? My population here next year is composed of individuals that didn't go anywhere, individuals that came to the population, and the new allele frequency is a combination of these two types of individuals. Okay? Now, the change in the allele frequency. The change in the allele frequency on the island, then, is equal to the allele frequency next year minus the allele frequency this year. And just like with population growth, it's easy to think about it as a change, right? If the allele frequency doesn't change, delta P1, Pi is equal to 0. If the frequency of the big A is bigger next year, delta Pi would be a positive value. If the allele frequency big A drops, that would be negative. Okay? All right, so what I can do is some basic substitution, right? If this is delta Pi, whatever, I could substitute this in and say that delta Pi is equal to this, 1 minus m Pi plus MPC minus Pi, well, that's still Pi, okay? The change in the allele frequency is equal to this, all right? Now, it's probably going to help to distribute things out first, and then we can group some terms. So let's go ahead and do some distribution here. So this would equal, change in Pi, sorry about that, is equal to Pi minus MPI plus MPC minus Pi, right? And that means that delta Pi is equal to negative MPI plus MPC. I'm just going to flip those. MPC minus MPI. Okay? And that brings us to this, which is M times PC minus Pi. Right, as before, you don't like the math, ignore all of this stuff, just move directly to this piece right here, right, that gets you around the problem. And the value of this is that if we set delta Pi equal to 0, what we're really asking is, what would cause the allele frequency to not change from one year to the next? What would cause the allele frequency to stay the same? Right? And that can happen one of two ways. Either m equals 0, well, the allele frequency can stay the same from generation to generation if migration doesn't occur, which would mean that m is equal to 0. Or, if the allele frequencies in both locations, the continent and the island, if they have the same allele frequency, migration would have no effect on the population's allele frequency. So we're using this equation initially to ask, well, what sorts of things cause allele frequencies to not change if there is no migration, or if allele frequencies are the same in both locations? Okay? Then we could take it from the other side. What would cause allele frequencies to change a lot? That is, what would make this delta pi a very large value? Well, that could happen if the number of migrants, or the proportion of individuals in the population that migrated to the population, was very, very large. Then I would expect a large delta pi, big effect on the allele frequency. Or if the difference between the two allele frequencies is very large, the larger the difference in frequencies between the two populations, the bigger the change in allele frequency is for the population. Is that okay? All right. All right, just trying to think my way through here. Again, trying to play around best with the time so that we don't run over. And I think what's probably best here is I'm going to go ahead and stop the lecture here. I'll make up the time in another lecture. But what we need to do next is the effect of natural selection on allele frequencies. Okay. So I will set this up now, and then next time what we'll do is play around with some simulation models. I'm thinking I have to reorganize a little bit how things are projected. I'm going to use this screen to project on so we can do the simulations. But let me go ahead and lay out the basics of the simulation model, and that way we'll be ready to go with it next time. So, with natural selection, the idea is that certain genotypes have higher fitnesses than others. And what that basically means is that these genotypes have an ability to leave more or less copies of their alleles into the next generation. So the notation we're going to use for fitness is W hat. This is relative fitness, right? And I'm going to subscript it like this, or like this. So this is the relative fitness of the homozygous A1. This would be the relative fitness of the heterozygote, and this would be the relative fitness of the homozygous A2. Okay? So what we'll do is use these fitness values to alter the number of copies of alleles that each of these genotypes leaves to the next generation. Okay? All right, so I'm going to cut it here 10 minutes early. Next time when we meet, I'm going to go ahead and start the simulations with you, run through those, with the idea that I'm going to make up this 10 minutes at some other point. All right? Take care. Bye.